Hi everyone, we are Team 4 and today we will be discussing our project Defending Against Adversarial Attacks. Machine learning models perform very well but are vulnerable to adversarial attacks. An adversarial attack is when someone purposely disrupts a machine learning model and causes it to perform not as intended. There are many types of adversarial attacks, but one method is the fast gradient sign method. As you can see, as we vary epsilon, the performance of classification for VGG16 drops dramatically. This is a very serious problem, as any system that relies on a machine learning model can be tricked by a bad actor into doing things that it's not supposed to be doing. We aim to re-implement visual concepts in compositional voting, and then to evaluate how the compositional model performed on adversarial images. To do this, we first needed to extract internal representations from VGG16 and call these extractions visual concepts. Then, we needed to evaluate the visual concept's ability to detect semantic parts of objects. And finally, we needed to create a compositional voting model using these visual concepts as building blocks. Unfortunately, we were unable to implement this last part, but we will discuss what we were able to. For our dataset, we used the Pascal VOC 2010 dataset as well as the vehicle semantic part from Pascal part dataset. From VOC 2010, we used a subset of the dataset and only used the vehicle classes. In total, this was 3,351 photos. The vehicle semantic dataset had masks corresponding to semantic parts of the vehicles from VOC 2010. For example, semantic parts annotated include wings on airplanes, windows on cars, and wheels also on all the different vehicle classes. This is just a subset of the different annotations that we were given. Next, we had to create our visual concepts. The visual concepts were created by feeding training images into VGG16 and then extracting feature vectors at the max pool 4 layer of this model. After collecting all these feature vectors, we clustered these vectors into 200 512 dimensional clusters and considered each centroid as a visual concept. Next, we had to create our positive and negative feature vectors. To do so, we fed mass images of a specific class into VGG16 and extracted feature vectors at the max pool 4 layer. Positive feature vectors corresponded to feature vectors created by images with positive masks. Positive masks were simply the union of the semantic masks, while negative feature vectors corresponded to feature vectors created by images with a negative mask on them, which was the inverse of the positive mask. So, in order to determine if a visual concept fired, we defined a visual concept to be firing if the difference between the feature vector and a visual concept fell below a threshold. Given this definition, if a visual concept fired on a positive feature vector, we consider this a true positive, while if it fired on a negative feature vector, we considered it a false positive. In order to evaluate our visual concepts, we created a set of thresholds T and looped over all the feature vectors and all the visual concepts and kept tracks of our true positives and false positive rates. After this, we chose our best 10 and 50 visual concepts. On the right, you can see the heat map for the firings of the visual concepts on the positive and negative feature vectors given the threshold range. Unfortunately, as you can see from the precision recall curves, our visual concepts have some predictive power, but not much. For our 50 best visual concepts, we had an AP of 0.56, while for our best 10 visual concepts, we had an AP of 0.57. The ROC curve also confirms this. The orange line indicates a classifier with no predictive power, and as you can see, our curve deviates from this, but not too much. In conclusion, for the final report, we hope to create visual concepts that correspond more strongly with semantic items. Thank you for watching this presentation.